So as I said, last but not least, Flori Bunea from Cornell will talk to us about fast minimax adaptive procedure for topic models with an unknown number of topics.
All right, thank you, Philippe. Thank you very much for organizing such a wonderful workshop. And thank you all in this room for being in this room and not outside. It's a beautiful day today. So let me get going pretty fast here. So I'm going to talk today about a class of models that's been very well, I should say, studied in computer science, in computational mathematics, information science, and used in lots of areas of applications. And what's missing from that list is probably statistics or statistical theory. Perhaps that's something that's worth looking at. So very concretely, I'll talk about topic models, and my interest in them is in staying with the theme of the workshop is to see if we can find procedures that have good that are statistically optimal in some sense, and my sense is going to be minimax, that can be done in polynomial time, the estimators, that is. And the talk is joined with my collaborator Martin Weckham, who's sitting somewhere in the room, and with our graduate student at Cornell, and I do not have pictures. I'm so sorry. Next time I'll go there. So the agenda is the usual agenda, with a small detour here. I'll define topic models. I've learned that conditional on the room, in which I give a talk on something like this. 50% of the people know intimately well the topic models, what a topic model is, and 50% have never heard of it. So instead of apologizing to one of the halves, I'll actually take some middle approach and define them. I'll explain why I want to look at them again, and rather than giving you a big overview, this is weaved in throughout the talk. For those of you who have never heard of topic models, let me just say I'll come up with an estimator that I claim is new. For those of you who have heard of these models, I'll just show that if you exploit some structures, you can do something altogether different from what other folks did. So it's not what I'm going to present is not a variation of what you've seen before, unless you've heard it from me. And I will try to. So the motivation for a new algorithm was triggered by looking at the optimality of the existing estimators, optimality properties relative to minimax, and I will explain what's out there, at least from what I know. Maybe I have not seen everything in this enormous literature. Is not minimax optimal. So the idea is find a new method that gives you minimax optimal estimators in topic models. So let's see what I mean by that. I'll start by stripping these models completely from a certain type of jargon, and then I'll add in the jargon. So if you have very simply n independent and not necessarily IID, and there's a key here, I'll be adventurous, I'm not going to do IID, I'm going to do independent. So if you have n independent multinomials, and you think, however, that they are somehow related, that is, the cell probabilities of each multinomial, of all these n multinomials are related, then you have many avenues, and one of them is via what is now known as topic models. Now I'm going to start adding terminology that comes from text mining, where these models, well, have been first called topic models. And I'll tell you where the topic comes in the model. Imagine that you have n documents. So that's the example, the standard example that comes with the description of this model. You have n documents. And each document is written using p words, or a vocabulary of size p, and you do not want to read all these documents, each document in its entirety, so you take a sample of words from each document. Once you take the sample, you record the observed frequencies per word, you put them in a vector, so that's a p-dimensional vector. There are p categories, p words, and then you stack these vectors one next to each other corresponding to all the n documents, and you've got your data matrix. So the expected of x in this extremely simple mechanism, if you believe that your data is generated by such a mechanism, so the expected value is the pi matrix, is the matrix of cell probability. So now we are going to do, borrowing information across n documents. We are going to model the entries of this pi, because we believe that somehow these documents, if you will, are connected, and what's going to connect them? The fact that each of them is probably going to cover up to k topics. We don't know. Each topic may be tangentially covered in a document, and maybe the main topic of the document. All right, so pi ij is the thing here where I'm going to define the model, is the entry. So it's an informal. The first line is an informal writing of Bayes rule. So pi ij is the probability that you see a word j in document I. First line Bayes. Second line, the topic model assumption that says that the probability of a word j occurring in topic k is the same across documents. So that's an assumption that's it as the beginning and the end of the topic model formulation. You don't have to have multinomials, but I just want to be very clear. You can have some other models for your count data, but let's just stay with multinomial for this talk. So very good. Once you've accepted that that may be an interesting way of modeling, all I'm saying here is a non-negative matrix factorization, although I do not want to talk about that. I simply assumed that pi is once again is a p by n matrix. Each column contains the cell probabilities associated with one document, and the cell probabilities, the cells are the words in the vocabulary that I have somewhere available to me. So I'm assuming this is the composition, and I'm adding in jargon once again, just so that I don't keep repeating the dimensions of the matrix. Probably the jargon helps keeping the talk focused. So the matrix A is called the word topic matrix. The matrix W is called the topic document matrix, and we don't know either of them. And also in this talk we are not going to know the number of topics. So, if you will, we don't really believe that the model holds. Let's say perhaps an approximation holds, but even if we believe that it holds exactly, it's a little unreasonable to also think that we know the number of topics. They are just a construct of our mind. So, let's not know them. The target of this talk, you can be interested in various aspects here. That today I'm going to be interested in the word topic matrix A, and the goal is, when I've mentioned minimax, what's going to be minimax optimal here. I'm going to try to estimate this A in a minimax optimal fashion, and I'm going to have to derive and explain what that means. But the key here is I also want to stay with the theme of the workshop, to do it in a fast way. So the model is once again very well known. I will give very little references, because if I start giving references, then I will give a talk on references. So I'll just refer you to an overview by Bly. And here is an example, just to make sure everybody's on the same page with notation and goals of the talk. Just to re-emphasize why this type of models are called topic models. So let's n here is the number of NIPS articles. So each, I look at lots of NIPS articles, and I'd like to know what topics they cover and what words are associated with topics. You can make any story you want here, but what I'm trying to draw your attention, I would like to draw your attention to, is why I want to estimate A. What is it? If I estimate A, what do I learn? Well, I will learn, so this, what you see here, are words. So what goes vertically is the number of words, so this goes all the way down to P. What goes here is the number of topics, and here I put some names, and this ordering in, say, the first column is the top words appearing Bayesian topics, and we need a rule to declare something top, and top is the largest values in one column of A. Naturally, I don't know the labeling of the topics is only identifiable up to permutations. So since I've just started to talk about identifiability, so that's the model. Very good. So if I want to estimate A, In the decomposition, from this decomposition, naturally I run immediately into identifiability issues if A is of interest. If I can live with the fact that I want A up to orthogonal transformations, then I should stop here and ask Matthew to use empirical base, and you know, everybody's happy. If I want to identify these things, if one wants that, one is forced into making assumptions that are sufficient. I claim that they are almost necessary, but let's just say that they are sufficient for now. And you can go various ways in this point, but the type of assumptions that I will make, once again, staying with the theme of the workshop, have scalability in mind. So at some point I'm going to estimate this guy A, and if I make my life slightly easier, I can estimate it faster. It's as simple as that. But don't think that I'm trying to make my life very easy. So this is kind of minimal, but I was talking to Peter Rickel. He likes to call this a prior, that I have this prior thing. So there are two assumptions here. If you want to look at this decomposition, they are called in the CS literature or machine learning literature the separability assumptions. If you cross the bridge into statistics as identifiability assumptions, so you need to say something about A and about W. The famous and infamous assumption here is the anchor word assumption, which you can love or hate, but I chose to love it. The anchor word assumption says that there is, for each topic, there exists at least one word solely associated with that topic. So for instance, if the topic is Bayesian literature, then I believe that the word posterior is only associated with Bayesian. So we can debate this, but we can debate this fact, but we can I think agree that although that may not hold exactly, it will hold approximately. So that is, it's a much higher. You see the word posterior in a Bayesian type paper much more frequently than not. All right. So that's that. And you can also, you need to say something about W, and here is a very, very, very mild assumption to start with, which simply says that, look, if I want to have K topics, I also don't know how you know, they need to be different if I call them different topics. It's as simple as that. And one way of doing it is to assume that the matrix W has rank K. You can assume less. You can assume, you know, that there are some simplicial. Anyway, bottom line is that's kind of what you want to do. I'm learning that if you go to higher order tensors, for identifiability. So what I will show you is that, sorry, let me take a lateral step here. I will show you in a second, and under these two assumptions, and a third assumption that's needed for K is unknown, you can reconstruct uniquely A from some functional of the data that involves pi. If you are willing to do this reconstruction from third order tensors or some higher order functionals, if you will, higher than 2, higher than a covariance type matrix, you may not need the anchor word assumption in some special situation. So I don't want to get sidetracked. So I think the gist of what I'm trying to say is that there is a lot here that can be said, but if you are in this exact setup that I'm explaining to you, I don't think there is much leeway if you want identifiability, unless you are Bayesian. And, so I'll continue to tell you the high-level approaches. So if we have this topic model and we are interested in it, okay. If we assume that we have these anchor words, that if we are happy to assume that we have anchor words. And we assume that K is known, the problem has been solved, essentially, in terms of identifiability and in terms of some quantification of the error that you induce by estimation. So, but in terms of identification, it has been solved, and here are the literature I know. Once again, I'd be very happy to hear more references for this particular setup. Once again, I'm aware of very many related setups, but that's this, yeah. Okay, so what's happening here is something that looks a little, it looks very simple. What it says: find the set of anchor words. These anchor words anchor the topics. You would think that once you figure out, what the anchor words is, you'll also figure out what other words are there associated to a certain topic. So that's the high-level idea. You first find the anchor words, and then you estimate the rest of A, which is the word topic matrix. Okay. So there is a problem here. Sorry, I forgot to say how you do this, because this is the thing that is difficult to extend when K is not no. This is totally high level, so if you've never seen this, then you are not going to follow much of what I'm saying. But if you have seen it, pay attention to this line. So what, in some way, by staring, as I said, the functionals of this functions, I should say, of pi, which is the probability matrix we are trying to factorize. So if by looking at things like this, you look at some rows, and you can see that somehow some rows are the convex combination of others, and all of a sudden you reduce the problem of finding the anchor words to that of finding the k vertices of a simplex. So if you don't know how many vertices you are looking for, I'm trivializing the issues here, it's difficult to extend this line of approach. This line of, so we should do something slightly different, or one should do. There are ways of relaxing things in many directions, but since with that difficulty in mind, rather than trying to squeeze more out of that particular observation, that under the anchor word assumption some rows in some matrix are linear combination of others or convex combination of others, we decided to take a completely new view of it, and that's the new view. So if you don't know the number of topics, we are still going to assume make the anchor word assumption. I'm still going to assume that I have different topics, otherwise we are not going to do anything. But I'm going to assume that they are sufficiently different. That the sufficiently different is a tricky kind of thing. So by assuming that the rank is k, that's an n by k matrix, I'm assuming that some rows or columns, whichever way you want to look at them, are not parallel. So what I'm saying here in this assumption, do not take in the form, please do not try to read it. I'm simply saying that the cosine of an angle is strictly smaller than 1. I mean, I've already assumed that it isn't 1, but it's strictly smaller than 1 in a particular way. And that's the new thing here, to say, look, on the one hand, there are extremes of this model in which people assume that the topics are orthogonal. They have nothing to do with one another. Okay, and I am here with this assumption somewhere with B, somewhere in the middle. Look, they are not orthogonal for sure. They are definitely related, but they are related. I have to control how related they are. They cannot be arbitrarily related, as A would say. So that's the thing, and that's what allows everything that follows to be completely different than what's been done. If you are willing to make that assumption, then you are in business. So what's happening here is the strategy will be more or less the same, but what we are allowing, I forgot to say, we are allowed to, from a practical perspective, if you buy this whole anchor word idea, you know that probably there are more than one word solely associated with one topic, for sure. And so what I'm going to show you is that I can also find all the words associated with one topic, and therefore find a partition of this anchor set, and the number of groups in the partition is going to give me this k, which I didn't know to start with. And then once again I will do some linear algebra. I will see that that's all there is to it, to find the word topic matrix, which is my goal. Okay, this is just to show that there isn't, it's not very difficult after you actually look at it for a second. So what we have is, once again, this is the factorization we are after. There are two steps to this problem. One is renormalize, rather important step. Always, the renormalization of everything is put under the carpet. That's kind of, if you don't do it, you don't get a starting point, trivial as it may sound. So you consider some renormalized versions of pi a and w such that they have row sums equal to 1. I'm sorry, I forgot to write that this pi tilde equals a tilde multiplied by w tilde. So I take an analog of this, and I reduce the problem of finding the anchor words used that are defined relative to a. So an anchor word corresponds to a row in a k-dimensional vector that is proportional to the canonical basis. So it's a 0.7000. So that's what the anchor words are. So this the same structure of rows of a that the type I'm interested in is present in a tilde. I will do that. I'll find this particular type of rows by looking at what I call the main character here, and it's I don't know, pi tilde square, if you will, something like that. And the assumption that I have made on the previous slide, and the only new assumption, is simply saying that it's impossible to follow if you don't know what these things are, but it just says that the off-diagonal elements of a matrix are strictly smaller than the diagonal elements. So you'll have to just, it's not diagonal dominance or anything, but that's what this is. Okay, so that's, if I can finally start my talk now, so that's the setup of everything. So what's interesting about this is that we can give an if and only if characterization of the anchor word set. So there is something that, once again, you shouldn't take in. I will explain to you with a toy example that shows you if you do something, if something is an index of an anchor word, then that's if and only if something else happens, and that's now what that is. So let's do it. That's the only thing that I'll explain in detail of how under my assumptions. So here is A, just to be clear of what an anchor word is. So the first 4 rows of this A correspond to anchor words. The first 2 are associated with the same topic because they have non-zero elements in the same position, and the other 2 are associated with other positions, with other topics. So the way you do it, you form this matrix R. Just believe me that you can form it, and it's something that's estimable from the data. So you form the matrix R, and then you go like this. You simply go and look at the maximum value per row. You go row by row. You look at row 1. You see what's the maximum value in row 1. And you notice it's 132, but it corresponds to 2 column indices, 1 and 2. Now you go down column 1, see if 132 still survives the test. If it's still the largest on this column, it does. Continue. Do the same with the second. It survive the same test. 132 is the largest. So this 1 and 2 are, I declare them according to my if and only if characterization, I declare them as being anchor words, and more importantly, anchor words associated with the same topic. Here is how it fails. I look on row 5, down row 5, the maximum element is 115. It's not the maximum per column. I declare 5 not be anchor word, once again via that if and only if characterization. This very simple, trivial idea allows me to do it. So the important thing about, so this is still population version. This is about identifiability, the fact that I can reconstruct A uniquely at the population version. And then what I'm gonna do is I'm gonna move to the sample version and just use plug-in estimators and do a little more work. So the number of topics comes out automatically from this algorithm. So it's not an input, that's all. And once again, there is a theorem that says that works. After you find, so if you know this anchor word business, if you can find them, which we have just done, then once again, you don't need to look into this, but essentially you can reconstruct the word topic matrix immediately. So what we give a closed form expression for A that shows A is equals to this, and this is is just a function of pi. Pi is the input of the procedure and of the anchor words. And so once again, all this is closed form, and the only challenging thing is taking the inverse of a matrix. So this is just understanding the model structure and doing linear algebra. And that's just a simple thing showing that, well, it works. It does exactly what I said it does. So for the estimation part, not much in terms of algorithm change. It's exactly what I just said. You find the anchor words and then you stare at the matrix and you figure that you can actually almost find it in closed form, A, the target that you want. So we want to make sure, but however, when we start estimating things, we want to make sure that we are somewhere near some optimal rate in this model. So we started out with that. And to our surprise, other folks who did similar things are really far from the benchmark. So the benchmark is very anticlimactic, if you wish. I have is the parametric rate. I have a model with pk parameters. I have a sample size that's essentially n, capital N. Capital N is how many words I see on each document. I have n documents. You can have different n's per document, just so that I keep it clean here. So that's the words that can happen to you in say the 1 infinity norm. What's the 1 infinity norm? That's the 1 infinity that's defined here. It's simply the L1 norm of each column and maximum over columns of the matrix A. So let's do the estimation. So the only thing that's noteworthy about estimation is the algorithm finds once again first the anchor words. In order to do it, it looks at maxima on the row of this matrix. In the population version it was called R, now it is called R hat. Naturally there will be values, and you look for the maximum values, some values that are pretty large, and you know, you take a few that are close enough. What close enough is, is relative to an entry-wise error. That's a kind of a tuning parameter here, and the word they should look at is the word estimable. So we are not playing the usual game in which we say, well, we threshold the soup norm difference between R hat and R. We can do this because we are in a very simple setting. We have assumed, the second I moved here, we have really assumed the multinomial distribution is kicking in. We can extend it, but right now that's what it is. And our graduate student was very excited to estimate this many threshold levels. So at the end of this thing, you get an estimator of the number of groups, of the number of topics, and let's see there is something interesting. Usually people kind of, you know, start nodding off at this type of support recovery, the support recovery part of the talk, but this is not the usual one, or it is, okay? I'm telling you it's not the usual one. What I mean is, if you have looked at this problem, you know. If you have not looked at this problem, I'm telling you that recovering these anchor words, if you believe that they exist, and if you believe that an algorithm should use that assumption in its construction, so if you make this leap of faith, so that's the difficult problem in this problem. And so what we want is, what we do not want is to make any kind of assumptions on the strength of the signal in the matrix of probabilities A that we are recovering, because they are, you know, that's gonna be too strong for this type of problem. It's too strong in general. So what we do is we can guarantee that if we make mistakes, so without the usual assumptions that are necessary if you want exact recovery, we make the least taxing mistake. So what I'm trying to say is that we are after recovering anchor words, that is, things that look like this, and we allow for the possibility of introducing, of declaring this guy an anchor word, but the important thing is that the large value in the what I call quasi-anchor word is in the same place as the large value of the anchor word. That is, they are essentially associated the same topic. So does that, and if it's not an anchor, is out and is correct, and some partial results have been obtained in 2013 by Bitorf in a slightly, you know, less general framework, but for K known. So this is by the way without K known. That's the whole thing. So now we are estimating this word topic matrix. The only small thing to say is that I told you that there is one thing: you have to invert a matrix. And you have to be careful how you construct, a little careful if you are, for a rate purpose, of how you construct this inverse. So it's just a small variation on existing climb type estimators of precision matrices. And at the end of the day, if you put all together all these things, here is how we estimate A. We estimate these anchor words, and that's optimization free. The estimator of A just involves this computation of an inverse that can be decoupled in k hat, k in general, but I've estimated k hat linear programs, each in dimension k hat. We have a refined type tuning parameters situation. We are in such a situation, and at the end of the day, you have a stable algorithm, and it's polynomial time p squared. I don't know. Hard to tell how precise this is. And this is the slide that contains the reason we started to look at this problem, and it's it's a small print, read the fine print. So the problem I've just shown, right? The solution has this solution A hat, and which is once again A is identifiable up to permutation. So I'm taking the minimum over permutation, so up to labels, and you get this particular expression here, which under some assumptions makes this RK disappear. So there are, of course, you can imagine all sorts of adversarial situations where this RK destroys the minimax bound. The minimax bound is just this ratio here. So things are probably not surprising that you need to make good assumptions if you want to get good results. But what was surprising to us is that the algorithm of Aurora et al., which is very nice. We like them. We like the algorithm. We like everything about them. What we don't like is that even if you are not into the minimax universe, if you have a rate that's p squared suboptimal, I mean, so their rate is this thing multiplied by p power 2. So then you start thinking maybe we can do something else. So that's really where, truth be told, where our interest in this problem started, from this point backwards. So I should go backwards. One very small thing, just to further say that we like existing work on this, but and also to re-emphasize what's important here. What you see in the left-hand side, it's some curves. The lower, of course, we want that curve to be as low as possible. Naturally, ours are the lowest, and the top is the competitors. If you can't see probably you can see the vertical axis. The differences are very small, so everybody is very happy there. These are happy curves. The error increases as the number of topics increases. This whole talk that I gave allows the number of topics to grow with the number of documents, so on and so on. So everything is great. Oh, not okay. With one small difference, just to brag a little bit, that the top curves, the existing good literature that on which this is based, inputs through k, ours estimates k and still does better, of course, right? Okay, so the thing is, why am I making such a big deal about k? Well, I mean, there are several levels of belief that we've applied. First, we believe that the multinomial model is good. The second, we believe that we should have anchor words. And now, if we also believe that we know how many topics there are, we are becoming very strong believers. Let me put it like this. So, if you what happens if you misspecify k? Since I chose to talk about k unknown, and I'm making a big deal out of it. Yes.
Assumption of very different.
Oh, this is it. This is the assumption that makes everything go. I don't. Yeah.
Is that assumption an additional one?
This is the only additional assumption to what people have used. Yeah.
Is that why you get rid of that terrible p?
Yes. I mean, but why can you give rid of it? It's because we can estimate these anchor words in a good way with guarantees, and the whole thing snowballs in a good way.
The first step.
The first step.
Algorithm hinges on this distinguishability between the different
Yeah, that's exactly the finding the anchor words. Yeah, that's the thing. Without it, yeah, and after that you don't need it. If you can find the anchor words in any other way, we no longer need that. If you give me the anchor words, that's not needed. Thank you. Right, and so here is my favorite plot. My graduate student, our graduate student had the ball doing this. It's a random guess versus other people, including us. So what happens with this type of algorithms? They are very sensitive to the misspecification of k. So green is random guess. So we took a matrix A, we filled it in with uniform 0, 1, scaled it so that it's what it should be. And the other two are these good algorithms of competitors and of ours. Very nice algorithms in which we input k, but now we vary k, right? So the true k was, I believe, were the 15. So if you are somewhere between, if you miss by 2-3 units, it's fine. But here, what you need to see is that when the green bar is almost as high as the other bars, then basically whatever you do after a long time is as good as random guess. So that's how sensitive these things are to misspecifying k. The summary what I talked about is indeed the topic models, in which we introduced a new assumption saying that topics are sufficiently different in a certain way, and that allows us to come up with a completely different approach, which in turn allow us to estimate these anchor words precisely or with guarantees, which in turn had the effect of allowing us to get near minimax adaptive estimators, or at least to get rid of the extra p-squared term in the rate that was out there in the literature. And you can, and k is not known, and grows with p, grows with everything, everybody grows. So this is based on something that's on archive, and a more general model, much related to what Ian was talking about, is what in fact started this whole work on topic models, where we look at other aspects than in terms of our interest there was on clustering rather than distinguishing what variance component comes from where. But anyway, the second bullet, big bullet, motivated the first bullet. And thank you very much.
Any questions?
Go for it.
So, with a lot of these topic modeling algorithms, I'm always a bit curious what happens if the model is misspecified, right?
Yeah.
Because I mean, the topic model is a bit silly for real world
Sure.
text. I mean, my sentences may sound like a topic model, but most of yours don't.
So I had this conversation with Andrea Montanari. So after 2 hours, we decided that it's a matter of perspective, of heated conversation. But I, of course, agree with you. Do you believe that linear regression is out there for us?
No, not at all. But I guess so.
Right.
So maybe here's the result.
Okay, tell me.
Before it would be for exponential family models or linear regression, we know we're getting the best L2 approximation
Here.
or the best KL approximation.
No, I hear you. So I do not have. So I hear you. It's a serious question. So there are 2 levels to your question. One, okay, I have the model, I assume it, allow me, and I come up with allow, okay, and I come with an algorithm that doesn't use all these restrictions, anchor words or whatever, and I say, this algorithm that may work for lots of things works for the topic one. What you are, so you are not asking exactly this, you are asking, well, I think you are asking, can I come up with something that works for approximations of, more or less in that ilk. It was a curiosity for us to see if we assume everything, why are, these statistical guarantees so bad? Is there something special about it? So in other words, the answer to your question is in what we are doing now. But I don't know the answer. So this was step 0. Yeah.
I have a question. So in the end, all these topic models. Sorry, I missed someone.
Yes, you. Okay.
So,
the empirical. No, I want the empirical base question. It's coming. Okay.
You know it's multinomial? No, I'm kidding. So the question is that I have is, so every time people show us the topic models, they end up sorting the columns of the topic and presenting only the top 5, the top 10. Is there a sparse version of this where you would want the columns of A to actually be sparse? And
Yeah.
if you're going to make a conjecture in front of the camera,
Yeah.
would it be the same
Yeah.
parameter counting argument that would give you the minimax trait?
Here it is, the other deeply intellectual reason that you don't see sparsity here is because we had it in the other paper. So we said, you know, we know how to deal with sparsity. Let's just do the easy way out because we refer for sparsity. Yes, the answer is yes.
Typically, P is large, right? So you have lots of first, but very tiny probabilities, but they're not zero, not sparse.
Well, it's not.
But you could find this right when,
Yes,
when you do sparse PCA.
yes.
Expect that there's directions that have no variance, but you want to estimate.
Everything is tiny. Right?
No, he's talking about the, yes, it's possible. Let me answer.
The one way of thinking about that is that you expect that the differences in the word frequencies between topics
Yeah.
are really sparse. So you have these keywords that are much more frequent in that topic than in others.
Right. So the so
The sparsity is not on the frequencies, but it's on a difference. I don't know if that's.
it can be no. I mean, in answer to both Martin's comment and his question, all these things can be incorporated in the model rather easily, and then indeed you have to adjust the minimax rate to answer your question, which I guess naturally once you have this incorporated, it has to come in the lower bound and the upper bound is to match it, and so yeah, so something in that direction is the second paper.
So I'll come back to that question. So how sensitive is it to anchor words?
Oh, it's very.
Absence, if there's no if
Well, I don't know how to. I mean, this is since I'm on camera, as you say. If I hate being filmed, then okay, that's camera dear. I don't like you, but anyway, that's. I don't know how to prove identifiability. If you know, so I just don't know. So this is my conundrum. I like anchor words as much as what?
Bayesian.
He's a Bayesian. I know he's a Bayesian, but still, right? I mean, it's we can take it offline, and I can tell you all the other things you can do. But if you want to do this is what I was trying to say, which doesn't mean much. Yeah, I don't know how to do this. Please enlighten me. There are many members in the audience who know a lot about this. So if you know how to prove the uniqueness of factorization in this setup without anchor words, I'd like to hear it. If I assume the model, not if I take if I define an approximation in a different way as a solution of something.
So following up this question, if you have k-1 topics that have an anchor word, but one that does not, can you guarantee that you always recover the k-1s that have an anchor word?
Honey, look at the definition. For each topic, there is one. I mean, it's my assumption. I don't know what happens when it fails.
No, it's true. It's true. You get them. That algorithm does that.
Oh, you are asking about the algorithm. I thought you are. What are you about what are you asking? Yeah, yes, honey.
Maybe I can clarify.
Yeah.
We know that there are situations with parameters that are not identifiable, with functions that are not identifiable. So I think to some extent that's the question you were asking. I mean,
Yeah. And actually, is there an order? Is the order in which you're...
Oh, I got it. I finally understood what you're asking. An order. An order, like what kind of order? On what?
You're dealing with your columns from left to right.
Up to permutations. I don't
Oh,
know.
yeah, sure, but
the
that's it.
algorithm.
The algorithm. So you are saying I have the output, or you are talking about the input of what are you? So be precise.
Okay, I'm talking about the output, right? So are you're reconstructing?
Oh, yeah. We wave our hands at the end and do some sort of ad hoc that you can help me with, because you can estimate the permutation for me. Okay, so yeah, so we are exactly. No, so of course we do some sort of a refitting. We are trying to do all sorts of cross validation, no proof, nothing. But then again, until you came along, I had no idea how to do it. But now I understand. Okay. Yes, Lisa, go.
So I think this happens in any place where you look at overlaps, right? It happens in overlapping clustering.
Yeah.
I know it in overlapping community detection.
Yeah.
basically if overlaps are small, things work. As soon as the overlaps are bigger, they don't work, right? I think that's the distinguishability, the sufficient
Yes,
difference.
yes, yes, yes.
So, do you have any sense of how one could quantify that? Maybe in this application, or even more generally, because this amount of overlap doesn't really come into the bounds, right? We just assume it's small, and then we can.
We have, I mean, I do have a very precise idea. It's very, I mean, we have exact quantification. So here, if you, okay, I'll give the very clear answer here. So, okay, high tech. The new assumption basically says that this thing minus this thing is larger than 0. So that's, if you will, my definition of something, of something that controls this whole it could control overlapping clustering, controls this thing. When I go and estimate these guys, that 0, so I put this here, this is a 0, is of course going to be something. And I have the exact expression, so it has to go to 0, but I can tell you exactly how and when. And what I don't know, and that's my open question to myself, although that this particular thing that governs, like how different the topics are, goes to 0, I don't know if that particular rate is minimax optimal, if you really want me to get all the way there. So that's the only thing I don't understand, if I believe in everything else that I said I chose to believe today.
Questions? All right, so we're gonna have to thank Flori again and go to the poster session and wine outside.